Asymptotic order of growth. Our discussion of computational tractability has turned out to be intrinsically based on our ability to express the notion that an algorithm's worst-case running time on inputs of size n grows at a rate that is at most proportional to some function f of n. The function f of n then becomes about on the running time of the algorithm. We now discuss a framework for talking about this concept. We will mainly express algorithms in the pseudocode style that we used for the Gale-Shapley algorithm. At times, we will need to become more formal, but this style of specifying algorithms will be completely adequate for most purposes. When we provide about on the running time of an algorithm, we will generally be counting the number of such pseudocode steps that are executed. In this context, one step will consist of assigning a value to a variable, looking up an entry in an array, following a pointer, or performing an arithmetic operation on a fixed-sized integer. When we seek to say something about the running time of an algorithm on inputs of size n, one thing we could aim for would be a very concrete statement, such as, on any input of size n, the algorithm runs for at most 1.62 times n squared plus 3.5 times n plus 8 steps. This may be an interesting statement in some contexts, but as a general goal, there are several things wrong with it. First, getting such a precise bound may be an exhausting activity and more detailed than we wanted anyway. Second, because our ultimate goal is to identify broad classes of algorithms that have similar behavior, would actually like to classify running times at a coarser level of granularity so that similarities among the different algorithms and among different problems show up more clearly. And finally, extremely detailed statements about the number of steps an algorithm executes are often, in a strong sense, meaningless. As just discussed, we will generally be counting steps in a pseudocode specification of an algorithm that resembles a high-level programming language. Each one of these steps will typically unfold into some fixed number of primitive steps when the program is compiled into an intermediate representation, and then into some further number of steps, depending on the particular architecture being used to do the computing. So, the most we can safely say is that as we look at different levels of computational abstraction, the notion of a step may grow or shrink by a constant factor. For example, if it takes 25 low-level machine instructions to perform one operation in our high-level language, then our algorithm that look at most 1.62 times n squared plus 3.5 times n plus 8 steps can also be viewed as taking 40.5 times n squared plus 87.5 times n plus 200 steps when we analyze it at a level that is closer to the actual hardware. Big O, omega, and theta. For all these reasons, we want to express the growth rate of running times and other functions in a way that is insensitive to constant factors and low-order terms. In other words, we'd like to be able to take a running time like the one we discussed above, 1.62 times n squared plus 3.5 times n plus 8, and say that it grows like n squared up to constant factors. We now discuss a precise way to do this. Asymptotic upper bounds. Let t of n be a function, say the worst-case running time of a certain algorithm on an input of size n. We will assume that all the functions we talk about here take non-negative values. Given another function f of n, we say that t of n is big O of f of n. Read as t of n is order f of n if, for sufficiently large n, the function t of n is bounded above by a constant multiple of f of n. We will also sometimes write this as t of n is equals to big O of f of n. More precisely, t of n is big O of f of n if there exist constants c greater than 0 and n0 which is greater than or equals to 0, so that for all n which is greater than or equals to n0 bounded, we have that t of n is less than or equals to c times f of n. In this case, we will say that t is asymptotically upper bounded by f. It is important to note that this definition requires a constant c to exist that works for all n. In practice, c cannot depend on n. As an example of how this definition lets us express upper bounds on running times, consider an algorithm whose running time, as in the earlier discussion, has the form t of n equals to p times n squared plus q times n plus r for positive constants p, q, and r. We'd like to claim that any such function is big O of n squared. To see why, we notice that for all n which is greater than or equals to 1, we have q of n which is less than or equals to q times n squared, and r which is less than or equals to r times n squared. So we can write that t of n equals to p times n squared plus qn plus r, which is less than or equals to p times n squared plus q times n squared plus r times n squared, which is, if we summarize the constant, that will be p plus q plus r times n squared for all n which is greater than or equals to 1. This inequality is exactly what the definition of big O dot requires. T of n is less than or equals to c times n squared, where c is equals to p plus q plus r. Note that big O dot expresses only an upper bound, not the exact growth rate of the function. For example, just as we claimed that the function t of n is equals to p times n squared plus qn plus r is big O of n squared, it's also correct to say that it's big O of n cubed. Indeed, we just argued that t of n is less than or equals to p plus q plus r times n squared, and since we also have n squared which is less than or equals to n cubed, we can conclude that t of n is less than or equals to p plus q plus r times n cubed, as the definition of a big O of n cubed requires. The fact that a function can have many upper bounds is not just a trick of the notation. It shows up in the analysis of running times as well. There are cases where an algorithm has been proved to have running time big O of n cubed. Some years pass, people analyze the same algorithm more carefully, and they show that, in fact, its running time is big O of n squared. There was nothing wrong with the first result. It was a correct upper bound. It's simply that it wasn't the tightest possible running time. Asymptotic lower bounds, there is a complementary notation for lower bounds. Often, when we analyze an algorithm, say we have just proven that its worst case running time t of n is big O of n squared, we want to show that this upper bound is the best one possible. To do this, we want to express the notion that for arbitrarily large input sizes n, the function t of n is at least a constant multiple of some specific function f of n. In this example, f of n happens to be n squared. Thus, we say that t of n is omega of f of n. Also written t of n is equals to omega of f of n if there exists a constant epsilon greater than 0 and n0 greater than or equals to 0, so that for all n which is greater than or equals to n0, we have that t of n is greater than or equals to epsilon times f of n. By analogy with the big O dot notation, we will refer to t in this case as being asymptotically lower bounded by f. Again, note that the constant epsilon must be fixed, independent of n. This definition works just like big O dot, except that we are bounding the function t of n from below rather than from above. For example, returning to the function t of n equals to p times n squared plus qn plus r, where p, q, and r are positive constants. Let's claim that t of n is equals to omega of n squared, whereas establishing the upper bound involved inflating the terms in t of n until it looked like a constant times n squared. Now we need to do the opposite. We need to reduce the size of t of n until it looks like a constant times n squared. It is not hard to do this for all n which is greater than or equals to 0, we have T of n equals to p times n squared plus qn plus r, which is greater than equals to p times n squared, which meets what is required by the definition of omega dot, with epsilon equals to p, which is greater than 0. Just as we discussed the notion of tighter and weaker upper bounds, the same issue arises for lower bounds. For example, it is correct to say that our function t of n is equals to p times n squared plus qn plus r is omega of n, since t of n is greater than equals to p times n squared, which is greater than equals to p times n. Asymptotically tight bounds, if we can show that a running time t of n is both big O of f of n and also omega of f of n, then in a natural sense, we found the right bound. T of n grows exactly like f of n to within a constant factor. This, for example, is the conclusion we can draw from the fact that T of n is equals to p times n squared plus qn plus r is both big O of n squared and omega of n squared. There is a notation to express this. If a function T of n is both big O of f of n and omega of f of n, we say that T of n is theta of f of n. In this case, we say that f of n is an asymptotically tight bound for T of n. So, for example, our analysis above shows that T of n is equals to p times n squared plus qn plus r is theta of n squared. Asymptotically tight bounds on worst-case running times are nice things to find since they characterize the worst-case performance of an algorithm precisely up to constant factors. And as the definition of theta dot shows, one can obtain such bounds by closing the gap between an upper bound and a lower bound. For example, sometimes you will read a slightly informative phrase sentence such as, an upper bound of big O of n cubed has been shown on the worst case running time of the algorithm, but there is no example known on which the algorithm runs of more than omega of n squared steps. This is implicitly an invitation to search for an asymptotically tight bound on the algorithm's worst case running time. Sometimes one can also obtain an asymptotically tight bound directly by computing a limit as n goes to infinity. Essentially, if the ratio of functions f of n and g of n converges to a positive constant as n goes to infinity, then f of n is equals to theta of g of n. Okay, 2.1, let f and g be two functions that limited of f of n over g of n, where n goes to infinity, exists and is equal to some number c greater than 0, then we say that f of n is equals to theta of g of n. Proof, we will use the fact that the limit exists and is positive to show that f of n is equals to big O of g of n and f of n is equals to omega of g of n, as required by the definition of theta dot. Since the limit of f of n over g of n when n goes to infinity is equal to c, which is greater than 0, it follows from the definition of a limit that there is some n0 beyond which the ratio is always between 1/2 times c and 2c. Thus, f of n is less than equals to 2 times c times g of n for all n which is greater than equals to n0, which implies that f of n is equals to big O of g of n, and the f of n is greater than or equals to 1/2 times c times g of n for all n which is greater than equals to n0, which implies that f of n is equals to omega of g of n. Properties of asymptotic growth rates. Having seen the definitions of big O, omega, and theta, it is useful to explore some of their basic properties. Transitivity. A first property is transitivity. If a function f is asymptotically upper bounded by a function g, and if g in turn is asymptotically upper bounded by a function h, then f is asymptotically upper bounded by h. A similar property holds for lower bounds. We write this more precisely as follows. 2.2. A. If f equals to big O of g and g equals to big O of h, then f is equals to big O of h. B, if f is equals to omega of g and g is equals to omega of h, then f is equals to omega of h. Proof. We will prove for part A of this claim. The proof of part B is very similar. For A, we are given that for some constants c and n0, we have f of n which is less than or equals to c times g of n for all n which is greater than or equals to n0. Also for some potentially different constants, c prime and n0 prime, we have g of n which is less than or equals to c prime times h of n for all n which is greater than or equals to n0 prime. So consider any number n that is at least as large as both n0 and n0 prime. We have f of n which is less than or equals to c times g of n which is less than or equals to c times c prime times h of n, and so f of n is less than or equals to c times c prime times h of n for all n which is greater than or equals to the maxima chosen among n0 and n0 prime. This later inequality is exactly what is required for showing that f is equals to big O of h. Combining parts A and B of 2.2, we can obtain a similar results for asymptotically tight bounds. Suppose we know that f of theta of g and that g is equals to theta of h. Then, since f is equals to big O of g and g is equals to big O of h, we know from the part A that f of is equals to big O of h. And since f is equals to omega of g and g is equals to omega of h, we know from part B that f is equals to omega of h. It follows that f is equals to theta of h. Thus, we have shown if f equals to theta of g and g equals to theta of h, then f is equals to theta of h. Sums of functions. It is also useful to have results that quantify the effect of adding two functions. First, if we have an asymptotic upper bound that applies to each of two functions f of g, then it applies to their sum. 2.4. Suppose that f and g are two functions such that for some other function h, we have f is equals to big O of h and g is equals to big O of h. Then f plus g equals to big O of h. Proof. We are given that for some constants c and n0, we have f of n which is less than or equals to c times h of n for all n which is greater than or equals to n0. Also for some potentially different constants c prime and nz prime, we have g of n which is less than or equals to c prime times h of n for all n which is greater than or equals to nz prime. So consider any number n that is at least as large as both n0 and n0 prime. We have f of n plus g of n which is less than or equals to c times h of n plus c prime times h of n. Thus f of n plus g of n is less than or equals to c plus c prime times h of n for all n which is greater than or equals to the maxima chosen between n0 and n0 prime, which is exactly what is required for showing that f plus g is equals to big O of h. There is a generalization of this to sums of a fixed constant number of functions k, where k may be larger than 2. The result can be stated precisely as follows. We omit the proof, since it is essentially the same as the proof of 2.4, adapted to sums consisting of k terms rather than just 2. 2.5. Let k be a fixed constant and let f1, f2, and so on until fk and h be functions such that fi is equals to big O of h for all I. Then f1 plus f2 plus f3 and so on plus fk is equals to big O of h. There is also a consequence of 2.4 that covers the following kind of a situation. It frequently happens that we are analyzing an algorithm with the two high-level parts, and it is easy to show that one of the two parts is slower than the other. We like to be able to state that the running time of the whole algorithm is asymptotically comparable to the running time of the slow part, since the overall running time is the sum of two functions, the running times of the two parts. Results on asymptotic bounds for sums of functions are directly relevant. 2.6. Suppose that f and g are two functions taking non-negative values such that g is equals to big O of f. Then f of f plus g is equals to theta of f. In other words, f is an asymptotically right bound for the combined function f plus g. Proof: clearly f plus g is equals to omega O of f. Since for all n which is greater than or equals to 0, we have f of n plus g of n which is greater than or equals to f of n. So to complete the proof, we need to show that f plus g is equals to big O of f. But this is a direct consequence of 2.4. We're given the fact that g is equals to big O of f, and also f is equals to big O of f holds for any function. So by 2.4 we have f plus g equals to big O of f. This result also extends to the sum of any fixed, constant number of functions. The most rapidly growing among the functions is an asymptotically tight bound for the sum. Asymptotic bounds for some common functions. There are a number of functions that come up repeatedly in the analysis of algorithms, and it is useful to consider the asymptotic properties of some of the most basic of these: polynomials, logarithms, and exponentials. Polynomials: recall that a polynomial is a function that can be written in the form f of n equals to a0 plus a1 times n plus a2 times n squared and so on plus ad times n to the d for some integer constant d greater than 0, where the final coefficient ad is non-zero. This value d is called the degree of the polynomial. For example, the functions of the form p times n squared plus q times n plus r with p not equals to 0 that we considered earlier are polynomials of degree 2. A basic fact about the polynomials is that their asymptotic rate of growth is determined by their high-order term, the one that determines the degree. We state this more formally in the following claim. Since we are concerned here only with the functions that take non-negative values, we will restrict our attention to polynomials for which the high-order term has a positive coefficient, ad, which is greater than 0. 2.7. Let f be a polynomial of degree d in which the coefficient ad is positive. Then f is equals to big O of n to the d. Proof: we write f equals to a0 plus a1 times n plus a2 times n squared and so on plus ad times n to the d, where ad is greater than 0. The upper bound is a direct application of 2.5. First, notice that coefficients aj for j less than d may be negative, but in any case we have aj times n to the j, which is less than or equals to the absolute values of aj times n to the d for all n which is greater than or equals to 1. Thus, each term in the polynomial is big O of n to the d, since f is a sum of a constant number of functions, each of which is big O of n to the d. It follows from 2.5 that f is big O of n to the d. One can also show that under the conditions of 2.7 we have f equals to omega of n to the d, and hence it follows that in fact f is equals to theta of n to the d. This is a good point at which to discuss the relationship between these types of asymptotic bounds and the notion of a polynomial time, which we arrived at in the previous section as a way to formalize the more elusive concept of efficiency. Using big O dot notation, it's easy to formally define polynomial time. A polynomial time algorithm is one whose running time is t and is big O of n to the d for some constant d, where d is independent of the input size. So, algorithms with running time bounds like big O of n squared and big O of n cubed are polynomial time algorithms. But it's important to realize that an algorithm can be polynomial time even if its running time is not written as n raised to some integer power. To begin with, a number of algorithms have running time of the form big O of n to the x for some number x that is not an integer. For example, in chapter 5 we will see an algorithm whose running time is big O of n to the 1.59. We will also see exponents less than 1 as in bounds like big O of square root of n, which is equals to big O of n to the 1/2. To take another common kind of example, we will see many algorithms whose running times have the form big O of n log n. Such algorithms are also polynomial time, as we will see next. Log n, which is less than or equals to n for all n which is greater than or equals to 1, and hence n log n is less than or equals to n squared for all n which is greater than or equals to 1. In other words, if an algorithm has running time big O of n log n, then it also has running time big O of n squared, and so it is a polynomial time algorithm. Logarithms record that log base b of n is the number x such that b to the x is equals to n. One way to get an approximate sense of how fast log b of n grows is to note that if we round it down to the nearest integer, it is 1 less than the number of digits in the base b representation of the number n. Thus, for example, 1 plus log base 2 of n rounded down is the number of bits needed to represent n. So logarithms are very slowly growing functions. In particular, for every base b, the function log b of n is asymptotically bounded by every function of the form n to the x, even for non-integer values of x arbitrarily close to 0. 2.8 for every b greater than 1 and every x greater than 0, we have log base b of n is equals to big O of n to the x. One can directly translate between logarithms of different bases using the following fundamental identity. Log base a of n is equals to log base b of n divided by log base b of a. This equation explains why you will often notice people writing bounds like big O of log n without indicating the base of the logarithm. This is not sloppy usage. The identity above says that log base b a of n is equals to 1 divided by log base b of a times log base b of n, which is equals to log base b of n divided by log base b of a. So the point is that log base a of n is equals to theta of log base b of n, and the base of the logarithm is not important when writing bounds using asymptotic notation. Exponentials. Exponential functions are functions of the form fn equals to r to the n for some constant base r. Here we will be concerned with the case in which r greater than 1, which results in a very fast growing function. In particular, where polynomials raise n to a fixed exponent, exponentials raise a fixed number to n as a power. This leads to much faster rates of growth. One way to summarize the relationship between the polynomials and exponentials is as follows. For every r greater than 1 and every d greater than 0, we have n to the d is equals to big O of r to the n. In particular, every exponential grows faster than every polynomial. And as we saw in table 2.1, when you plug in actual values of n, the differences in growth rates are really quite impressive. Just as people write big O of log n without specifying the base, you also see people write the running time of this algorithm is exponential without specifying which exponential function they have in mind, unlike the liberal use of log n, which is justified by ignoring constant factors. This generic use of the term exponential is somewhat sloppy, in particular for different bases, r greater than s greater than 1. It is never the case that r to the n is equals to theta of s to the n. Indeed, this would require that for some constant c greater than 0, we would have r to the n which is less than or equals to c times s to the n for all sufficiently large n. But rearranging this inequality would give r over s to the n which is less than or equals to c for some sufficiently large n. Since r is greater than s, the expression r over s then to the n is tending to infinite with n, and so it cannot possibly remain bounded by a fixed constant c. So asymptotically speaking, exponential functions are all different. Still, it's usually clear what people intend when they inexactly write the running time of this algorithm is exponential. They typically mean that the running time grows at least as fast as some exponential function, and all exponentials grow so fast that we can effectively dismiss this algorithm without working out further details of the exact running time. This is not entirely fair. Occasionally, there's some more going on with an exponential algorithm than first appears, as we will see, for example, in chapter 10, but as we argued in the first section of this chapter, it's a reasonable rule of thumb. Taken together, then, logarithms, polynomials, and exponentials serve as useful landmarks in the range of possible functions that you encounter when analyzing running times. Logarithms grow more slowly than polynomials, and the polynomials grow more slowly than exponentials.